chapter 19. So your next test will be 18 and 19, which is this one, and 19 is temperature. So we should start 19 today and finish it by, what is today, Wednesday? So we should finish it by Monday. So this chapter covers the temperature scale, ideal gas law, and expansion and contraction of materials that are heated or cooled. So predominantly we'll focus on this topic, okay? But we'll talk about the temperature scale and the ideal gas law quickly, but we're not going to dwell too much on the ideal gas law because in later chapters we're going to be doing a lot of it. But it's just kind of, the chapter just introduces it. So temperature scale, we got, of course, the Kelvin is Celsius plus 273, right? And then when Kelvin is 0, that's called absolute zero. Absolute zero. So as I said at the beginning of the semester, physics 2, the topics change, always, constantly changing. So then that's equal to negative 273.15 Celsius. And then when Kelvin is 273.15 Kelvin, that's called freezing point of water. So that's 0 Celsius. Okay, and then when Kelvin is 373.15, that's boiling point. That Celsius is 100 Celsius. So typical room temperature, we usually call it around 300 Kelvin. 300 Kelvin is room temperature. So it's an easy way to remember that is it's approximately 27 Celsius. And it makes this a nice rounded number. Okay? So when you go to physics 4 and you learn about Wien's law, actually, we covered that we don't really cover it in physics 2 too much, but I'll mention it when we get to that topic of radiation. But in physics 4, they go more in depth into Wien's law. When this was a topic that called blackbody radiation, when objects are heated to a certain temperature, they radiate the electromagnetic waves, right? And they radiate in all kinds of spectrum. So if we take the intensity of radiation as a function of wavelength. So we can make a plot. This is large wavelengths. Large wavelengths, and this is small wavelengths. So what would be the blackbody radiation spectrum of a 300 Kelvin object? Well, that would be like our body. Well, our bodies are a little bit hotter, right? What's our bodies? Our bodies are 37 Celsius, right? So we're 310 Kelvin. So that's body temperature. So we are Celsius about 30. Actually, it is exactly 37 Celsius, right? So nature has it that we are generally hotter than room temperature, right? So we radiate more into the room than the room gives to us. So we're radiating away a little bit more to the room because we also absorb from the room and we radiate to the room. Well, if we radiate to the room more than we absorb from the room, how does our body maintain homeostasis? How do we not, why don't we cool down?
Because the body's doing functions.
Yeah,
friction.
that's biology and I don't know. I'm a physics teacher, right? We are warm-blooded animals, right? Which means what? We don't take on the temperature of our surroundings. So what cycle do we use? Who are the bio majors here?
Well, I know this.
How do we maintain that 37 Celsius?
Well, all warm-blooded animals, I think most living creatures, there's this rule where energy is throughout the food chain. Energy is lost. 90% of energy is lost as you go down one step in the food chain. 90% of it is lost to energy, and 10% of it is actually passed down to the next line. So, for example, grass would start at like 100%, and then let's say a rabbit would consume all of it. But let's say something ate the rabbit, it would only consume 10% of the energy that the rabbit consumed from the grass. Because 90% of that energy was lost to the heat.
So by what we're eating from the surrounding, we're keeping a little bit of that energy, you're saying, in order to keep ourselves warm, warmer than our surroundings. Is that kind of what you mean?
Yeah.
That by eating the energy of the surrounding, we have evolved the ability to take that energy, dump it all out, but except keep some of it to keep our bodies warmer. You see? Maybe that, I kind of interpret what you're saying like that. We're keeping that temperature. So if we take the black body radiation of a 300 Kelvin, it's going to look something like this. So this is how much energy we're going to radiate into outer space. This is the black body radiation of a 300 Kelvin object. What wavelength does it peak in? See, this is called the peak wavelength. That's Wien's law. Okay, if we say Wien's law and we write it with a W, right? But in German, W is a V. And V is an F. Right? So you say Ludwig von Beethoven, not Ludwig von Beethoven. Right? V is an F in German. So Ludwig von means he's from the family of the Beethovens. Von means from in German. He comes from the line of the Beethovens, right? But W is a V actually, so Wien's law. And Wien's law is written like this. Million, the wavelength that you peak in depends on your temperature, right? And since we and the surroundings are roughly 300 Kelvin, what wavelength do we radiate in? We put 300 here, what do you get? That's going to give you, what is that? 10000, 10,000 nanometers. Well, what electromagnetic wave is that? Radio. From 400 nanometer to 700 nanometer is the visible spectrum. From 400 nanometer to 700 nanometer, this is red. This is blue or violet. So on this plot, it would be somewhere here, for example. You know, would be Roy G. Biv. Roy G. Biv. Violet, indigo, blue, green, yellow, orange, red. Right? And then you keep increasing the wavelength to infrared. So do we radiate red? No. Don't look at my t-shirt, which is orange. That's a different thing. That's because the orange pigments is absorbing everything but orange reflecting orange. That's not radiation. It's not radiating orange. You see? But our bodies radiate infrared. Okay? But now, if we go to the higher scale, go to 3,000 Kelvin, that's a star, right? So star, cold star, 3,000 Kelvin, what wavelength will it peak at? 1,000 nanometer. So which is roughly kind of the higher end of the red, right? So what does its spectrum look like? Will that star also radiate infrared? Yeah. But it's going to radiate a lot more in the red. So what color will it appear to us? A red-looking star, a red supergiant, maybe. You know. So notice what happens. The peak shifts this way from here all the way. If you go from 3,000 Kelvin to from 300 Kelvin to 3,000 Kelvin. The peak shifts, but it also goes up, because since that object is hotter, it will emit much more radiation, right? So our sun is how many Kelvin? 6,000 Kelvin. Sun is 6,000. So what is its radiation going to look like? It's going to go half of that. And it's going to go way up. Like that. So the sun is going to be brighter than a 3,000 Kelvin, and it's going to look yellow or orange, right? It's going to go shift this way. Actually, it ends up that the sun peaks in the green, but we see it as a yellow star because there's some absorption going on in the atmosphere.
Oh, wow.
Yeah, it's actually green. Okay, cool. So then we'll continue this topic on a Monday.